See a few more people coming in. Oh. All right, so I know it's getting kind of late in the day, and I don't want to torture you guys with too much more math, but there will be some in this, definitely. So first of all, let me say a little bit about me. All right, so I am I actually hold a kind of associate appointment. I have two appointments, one in chemistry and one in here in the Courant in applied mathematics. So I'm Mark Tuckerman. And while I spend a lot of my time here at NYU in New York, I also now am spending more and more time at the newest NYU campus in Shanghai, where I'm also building a research group over there. And the great thing about being a theory-oriented person is that that's something you can do anywhere. Now, as it turns, so I said that I have this dual appointment between chemistry and mathematics. It turns out I'm neither of those things. I am a theoretical physicist, as it turns out. And at the time, so I did particle physics for some time. At the time I was doing it in graduate school, the only jobs a particle physicist could get were Wall Street quant or taxi driver. And I figured I wanted to do science and math, so I migrated over to chemistry, where now I get to work on a variety of different things that you see kind of being animated over here. I don't know, one of them got lost. But we do a lot of work on peptide structure, so we're looking at peptides that can be used for novel medicines. We do some work in sort of traditional medicines, which is the area of molecular crystals and crystal structure prediction. And then I'm going to talk about some surface chemistry today a little bit. And we also do work on the sort of traditional physical chemistry things, aqueous solutions. Well, as a theory-oriented person, in preparing for this lecture, I kind of wanted to get a sense of what the perception is of what theory people do. So I went to the web and I looked for some answers to the question, why do we need people like me? Why do we need to do theory at all? All right, what is theory all about? And I found some interesting answers. Okay. I found this one, right? The purpose of theoretical science is to serve the practical needs of mankind. Now, if that isn't a vague answer, I don't know what is. That turns out to have been said by Descartes, so, all right, should be profound, but it's not. In fact, the most profound explanation of what theoretical science is all about is to give a higher sense of order to the facts as they're presently known, or to point to new observations that can be verified experimentally. I thought that's really good. Sort of the source of that turns out to be the author instructions for a kind of not so well-known class of journals called the Elsevier journals. Right? And then there's this definition called the structuralist view. The purpose of theoretical science is to put relational order into the observed phenomena. So these definitions are sort of getting to the idea of what theory people in the sciences are supposed to be doing. So to give maybe a better list of the things that we do, all right, I kind of compiled this list about what it is that we do, or maybe more importantly, what do we do with your tax dollars? Now, you all will eventually be taxpayers, and so you will want to know what is it that your tax dollars are going to in supporting someone like me. All right, so one of the things we're supposed to do is to devise mathematical models to describe complex problems. All right, so a theoretical physicist, theoretical chemist is often described as someone who turns coffee into theoretical models. Okay, of course, a model is no good if you don't have a method for extracting information from that model, for solving that model. So the other thing we have to do is to devise algorithms or procedures for solving the models. We need to interpret and rationalize with these models the experimental observations. And of course, the most important thing is we would like to be able to make predictions that suggest new experiments, new things that people can look for, new phenomena. And a larger goal, of course, is using just theoretical techniques, which means mathematics and computers. We want to design new materials or processes starting from first principles. And that really means starting from the basic laws of physics. Okay. Now, this idea of doing chemistry by computation actually has a lofty history. All right? So this is Joseph Gay-Lussac, 1808. All right? And people, if you study chemistry, you encounter his name as someone who contributed a lot to the early theories of just simple reactions, so stoichiometry. He said we're perhaps not far removed from the time when we'll be able to submit the bulk of chemical phenomena to calculation. Very interesting idea. Of course, he couldn't have envisioned the way that we do it today, which is really at an atom-by-atom level. All right? But that was sort of visionary at that time. Unfortunately, the party is always spoiled by some French philosopher who comes along and says something like this: every attempt to refer chemical questions to mathematical doctrines must be considered now and always as profoundly irrational, being contrary to the nature of the phenomena. All right? And unfortunately, theoretical chemists labored under that impression for a really, really long time. By the way, I should mention that this guy who said that, Auguste Comte, was what they call a positivist philosopher. Well, it turns out that the pendulum always swings the other way, and this guy, Paul Dirac, one of the great fathers of quantum mechanics, said that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are completely known. And the difficulty is only that the exact solution of these laws leads to equations much too complicated to be solved. So he was referring to the appearance on the scene of quantum mechanics, quantum theory, which really does allow you to do all of chemistry if only you could solve the main equation that comes up there, the Schrödinger equation. The reason that he said this, of course, is that at the time, that's how you had to do theory. All right? So whatever you couldn't scratch out on pencil and paper, you weren't going to be able to do. But now, we still do some of this, but much of what we do for theory is this. All right? We use one of these. That is an enormous supercomputer. That happens to be one of the computers at the Oak Ridge National Laboratory. It's called Titan. And it's a computer with, I think, literally millions of processors all working together to solve the basic equations of physics and give you answers that are hopefully interesting in areas like chemistry. Okay. Now, before getting into some of the science, let me just point to an interesting document that came out a few years ago. This is called the Materials Genome Initiative, and it was put out by the White House. Right? So we all recognize that guy, right? And what he said was, to help businesses discover, develop, and deploy new materials twice as fast, we're launching what we call the Materials Genome Initiative. The invention of silicon circuits, lithium-ion batteries, et cetera, are made possible, but it took years to get those technologies from the drawing board to the marketplace, and we want to be able to do it faster. So what he was calling for was an acceleration of the time from concept to product. And the way that he wanted this to happen was to combine the skills of those who do mathematics and computation and theory with those who actually do the experiments and also those who are engineers and actually create the products that they need. So, for example, the document is written for stakeholders in the materials development community from experimental and theoretical science conducting basic research. And over here, the new integrated design continuum incorporating greater use of computing and information technologies coupled with advances in characterization experiment will significantly accelerate the time and the number of materials deployed in replacing lengthy empirical studies with mathematical models and computational simulations. So all of these are just drawn right from that document that I showed you. And there's actually a paper on this stuff in Current Opinion of Solid-State Material Science, where the whole idea of the materials genome is sort of explained and at a scientific level. It's a really, really good paper. Okay. And maybe some of you are aware, in 2013, the Nobel Prize in Chemistry was given to these three guys. Okay, so that's Martin Karplus, that's Michael Levitt. Martin Karplus is a professor at Harvard and at the University of Strasbourg in France. Michael Levitt is at Stanford, and Aria Warshall is at the University of Southern California. And this was really the first Nobel Prize in chemistry that was given to theoreticians for what they did in the area of computer simulation. Okay, so what they did was they had a very nice technique called multi-scale modeling for treating complex chemical systems. So they did exactly what I said the theoretician needs to be able to do, to devise interesting mathematical models. Right? Okay, so the community is actually starting to recognize the importance of theory and mathematics in chemistry, even though this is a field that's been around for well over 30 years. Okay, so when I talk about the virtual chemistry laboratory, what do I mean? Well, I mean, using the computer and equations to get at interesting problems in chemistry. So what do we have in the shelf of our virtual laboratory? Well, okay, we have all the chemical elements that you might want. There's nothing dangerous for us to work with because it's all being done in the computer. So anything on the periodic table that you want, you can use. You have an unlimited supply of electrons because you just put them into the computer. And you have instrumentation. So our instrument is not an STM, it's not a spectrometer, it is in fact a big supercomputer. Okay? And what do we have the supercomputer do? We have it crunch on the fundamental laws of physics, and we apply them to chemistry problems. So what are those? Well, for example, nuclei of molecules can often be treated by just F equals ma. All right? What's F equals ma? Who knows? But whose law is that? F equals ma. You guys taking any physics? Newton's second law of motion? Okay, remember Newton's second law of motion. Newton's second law of motion is the law that says that something moving in a straight line will continue to move in a straight line unless acted on by a force. All right, and that's exactly what you see happening here. So, and the force causes a change in the motion of the particle, so it gives rise to an acceleration. So let me back up. ma is the acceleration, m is the mass, and F is the force that it feels. Well, it turns out that the acceleration is actually the second derivative of position, and the force is very much a function of where you are. All right, so the penguin doesn't feel a force until it gets close to the other penguin. There's an interaction between them, and then one of the penguins changes its motion. So force is a function of position. So in fact, what you have here in Newton's second law of motion, which governs how things move, is a bunch of second-order differential equations that you have to solve. Now, of course, when Newton came up with these, what he had in mind was to use it to predict the motion of planets. So for example, if I wanted to know how the Earth moves around the sun, I would use F equals ma to do it, and the force would just be the force of gravity between the sun and that planet, which in this movie looks like it's Earth. And you would be able to predict exactly what that orbit is. So that's where Newton's laws of motion actually come from. But it turns out that in chemistry, these laws are actually very useful. They turn out to be you can use them to predict the motion of every atom in your system. Where is everything going? So this is a little movie of an ideal gas. All right. So the only thing that happens here is that every particle moves on a straight line. You can see it doing that until it encounters a wall, and then the wall exerts a force on the particle, and it changes its motion. All right. So it's a perfect reflection type of motion. So the angle in is the angle out, and from that, you can predict all the properties of the ideal gas. Okay. Now, in chemistry, of course, if you've ever taken chemistry, what you learn is that, in fact, in order to calculate what these forces really are that go into this, you need to solve something called the Schrödinger equation, and don't worry too much about it. It just tells you really where the electrons are, and they govern what forces the nuclei exert on each other. The electrons modulate that force. So a solution of the Schrödinger equation gives you an electron distribution where the electrons are around an atom. This is what an example is called a d orbital. And it's a very, very complicated looking partial differential equation. All right? So in fact, this equation for the nuclei and this equation for the electrons, you can't solve them on pencil and paper. It is not possible. But if you have a computer, you can do it. Okay. And that's an example of what a solution to the Schrödinger equation will actually look like in a real chemical system. Okay, so this is a bunch of water molecules, and there's an acid dissolved in there. Okay, it turns out to be hydrochloric acid. The chlorine, I think, is back there. It's that pink thing. And then the H comes off, HCl, attaches itself to a water molecule and forms this thing called the hydronium ion. And that yellow stuff is the distribution of electrons in there. And that really comes from solving, numerically, of course, this partial differential equation. And from that, I could predict what every atom in this, or every atom on a water molecule, or every atom in the acid, what force it exerts on every other atom in the system. And from that, I could use Newton's second law to predict the motion. Okay, so let me come back to this example of the ideal gas and kind of show you what it is we actually might calculate in here. So one of the things we might do is we might say, well, all right, I know that the particles exert forces on the wall because the walls exert forces on the particles. So I might want to calculate the pressure in the system. And from the point of view of the microscopic motion of every atom in the system, I might calculate the average force divided by the area of a wall of the box. I might also calculate the temperature, which I just do from averaging the kinetic energy over all this motion. All right? And it turns out if you do that and you ask, how is the pressure related to the temperature? Well, you get the so-called ideal gas law. So who's heard of the ideal gas law before? PV equals nRT. Okay, you can get it directly from looking at the motion of every atom in the system. Now, this is a well-known result. So this is kind of a trivial example that I'm showing you here. All right? And of course, what we want to do is to take complex systems and predict much more interesting relationships like this. All right? But that's the kind of calculation that you might do to discover a fundamental law like that. Okay. So the first question is, how do we move atoms around? I said you can't solve the differential equations, so you have to go to the computer and tell the computer to do it. So instead of actually solving differential equations on paper, we discretize the time parameter in there, and then we put it on the computer. And in order to get the computer to do what we want, we need to tell it how to advance the positions based on the laws of physics that we have from one discrete time point, let's say at t equals 0, to 1 delta t, 1 step in time, 2 delta t, 2 steps in time, 3 delta t, 3 steps in time, et cetera, et cetera. Okay, so who knows what the thing is called that will do that for us? Anybody have a guess? The answer actually is in the Big Bang Theory. Well, if you can.
We have to create a database before you can write an alga thingy.
Algorithm. Easy Penny Allen Turing defined an algorithm.
Okay, so she's right. Well, he's right, actually. You need an algorithm of some kind. All right? So we're looking for an algorithm that will actually advance the positions based on the laws of physics. And in fact, one of the things that we might do is to say, okay, let's say I have positions at time t. And I want to predict them at a time little delta t, this delta t later. And we're going to assume that this step is small. So what I might do is I might use a Taylor series. Right? So I take RT plus delta t times the first derivative, a half delta t squared times the second derivative. And if I stop there, then the error that I make is going to be of order the cube of that time step. Okay? And turns out that everything that you see here, these derivatives, are predictable. For example, dr dt is nothing more than the velocity of the particle. Well, so that I have. And the second derivative is the acceleration, which is just the ratio of the force to the mass. And the forces I actually have as well. So if I put all that together, now I have an algorithm for advancing the positions from time t to time t plus delta t very easily. All right? And it's going to be accurate up to order delta t cubed. Turns out I can do the same thing for the velocities, and the only thing I need to do in order to get also delta t cubed accuracy is to take an average of the force at t and the force at t plus delta t. But I can calculate those two forces. I can really calculate them anywhere, and so I can get this average. Okay, and so here's a flow chart of the way the algorithm actually works. So you start with positions and velocities at some point, let's say t equals 0. You compute forces, so you actually get these things, usually by solving the Schrodinger equation. You advance the positions and velocities one step, okay? Calculate something interesting. And once you've done calculating something interesting, you're ready to go on to the next step. So you recompute the forces there, advance the positions, do another calculation of something interesting, and you just go around this loop until you have an entire trajectory, right? Like that ideal gas thing that I showed you. Okay, so actually here are two examples of calculations that use that basic idea. You're looking at here a protein folding, okay? And so every sphere on this represents an amino acid of some type. The red ones turn out to be hydrophobic amino acids. The green ones are hydrophilic, and the blue ones are prolines. All right? And so what this thing does is it folds up under the action of F equals ma and the laws of physics into what's called a little beta barrel structure. And over here, you're looking at a molecular crystal, turns out to be a benzene crystal, undergoing a series of polymorphic transitions. Okay. Now, it turns out that these two things, which look to be very, very different chemically, right? One is biological, one is some crystal thing, solid state chemistry, turns out that from the computational point of view, they are very, very similar. And what makes them similar is this thing. All right? So what this is a cartoon sketch of what the potential energy might be for a system of atoms like this and like this. All right? The potential energy just measures how much potential you have to do something as you move. All right? And what you might notice about this potential energy, it's a surface, first of all. Right? It's a very complicated surface. And it's a very bumpy surface. So there are a lot of local minima, a lot of hills that you have to climb. And in order to go from one minimum to the next and visit different conformations like this protein is doing, I have to be able to hop from one of these basins to another basin, then to another basin, then to another basin. From the energetic point of view, I want to be in these low energy configurations, but it's very hard for me to go uphill and then over the hill to get to the next basin. So this is actually a big challenge in computer simulations, is how do we make a system actually hop over an energy landscape like that? You know, when you're hiking, that if you try to walk over hills, all right, you have to expend a lot of energy to do it. Okay, so now I'm going to come to the interesting applications. So let me try to motivate it by saying one of the things that we're interested in is molecular crystals, and in particular for use in pharmaceuticals. All right, now pharmaceuticals. Why is molecular crystals an interesting issue in pharmaceuticals? Well, it turns out that when you ingest something, so when you have a dosage like this, it comes from a crystal that's actually been ground up into a powder. So what you're actually ingesting is little particles of a molecular crystal. And different crystals have different properties. In fact, any molecule can form any number of crystal structures, and those crystal structures have different properties. And the most important property from the pharmaceutical point of view is, does it dissolve in the environment of your stomach? Is it soluble? And if it's not soluble, then it's not going to work. And there's a famous case of this called ritonavir. It's an HIV protease inhibitor. And it exhibits something called polymorphism. So as I was saying, polymorphism just refers to the ability of a compound to form multiple crystal structures. Okay, so this was a multi-$100-million investment. That's the molecule that they came up with, and it's a protease inhibitor. All right? So it was originally dispensed in 1996, and they said no refrigeration was required. That's the structure of it. And it's supposed to go into the HIV protease, that's being shown here, and it's supposed to inhibit the action of that protease, which what it does is it carves up a long polypeptide chain into active viral particles that the virus needs. So if you gum that up, then this thing can no longer do that, and you just end up with immature viral particles that do nothing. So that was the crystal structure that was known, and that's how they were selling it at the time. Well, what was happening is that on the shelf, this structure of this molecule was converting spontaneously to this. I don't know how well you can see that. Do we have light control in here? It'd be nice if I could get the front lights off, actually. Okay, well, while she's looking, I will continue. So this crystal structure turns out to be really, really stable, all right? And so it wasn't soluble, it wouldn't dissolve in the environment of the stomach, and therefore it wouldn't function as it was supposed to. So they had to recall the drug in 1998. It took them 4 years to reformulate the drug, and then they went back to market with a version of it that didn't undergo this transition. But 4 years and millions of dollars were spent reformulating the drug. This is something you'd like to know before you go to market with your drug. And since doing the experiments on this it's very time consuming and very costly, it's an area where computation and theory and mathematics can actually play an important role if you have an algorithm capable of finding all these different crystal structures. Okay. Well, it turns out that other common drugs are also polymorphic. Zantac, which you take for heartburn, is very polymorphic. All right, so there's a couple of different forms. Turns out that the known forms so far are all bioavailable. So, good. You can go to market with both of them, and they both work. Aspirin, all right, acetylsalicylic acid, also is polymorphic. In fact, all the different structures of aspirin haven't really been fully characterized, so we don't know all the different forms of aspirin. Okay, well, this is such an important problem that there is a competition that runs every 4 years. It's run out of the Cambridge Crystal Structure Data Bank, and they want to encourage people who do algorithm development to come up with techniques for predicting crystal structures. So what they do is they give you a list of target molecules. These are all interesting pharmaceuticals. And they give you nothing more than the chemical formula. So they give you, and the structure. And they say you're supposed to come up with a way of predicting what the different crystal structures are that these molecules will form. And the one who gets closest, the group who gets closest, wins the competition. All right? And there actually is one going on right now, as it turns out. All right, so we've been interested in this problem and trying to find algorithms to predict these crystal structures. And it uses a concept that I like to call collective variables. Now, collective variables, when you think about a complex chemical system and all the atoms that you have in there, you have hundreds and hundreds and hundreds, thousands, even millions possibly, of coordinates for all the atoms in the system. So there's a lot of data that you have. Oops. It's all right. There's a lot of data that you have, all right? And you'd like to be able to represent that data in kind of a low-dimensional space, all right? And collective variables represent a way that you can do that. So for example, if I had a little peptide like this, all right, that's a bunch of atoms in there. They all have positions, and that's a lot of information. But the conformations that this thing can form can be characterized in terms of just two variables, two angles that are called the Ramachandran angles, phi and psi. These are dihedral angles. And if you plot what's called the free energy surface, all right, so free energy just measures the work that you need to go from state to state, and it's just the enthalpy minus T times the entropy, you get a picture like this. And the blue regions here show the favored conformations. So you can really characterize everything about this in terms of these two variables. In crystals, turns out you have a bunch of collective variables at work as well. For example, the shape of the box. All right, so if you ever learn about Bravais lattices, of course, this is one of the key things that you need to know. And that's characterized in terms of three vectors that just lie along the three axes of your box. You can calculate the volume from that. You might want to know how things pack. All right, so there are packing parameters that you can use. And you might want to know about how the molecules are oriented. So all of these things characterize the crystal, and therefore we can use them as a way of parameterizing or getting at a picture like this, a free energy surface. Okay, now once we've chosen our collective variables, then what we want to do is to calculate the free energy, because that's going to give us a thermodynamic ranking. It's going to tell us which crystal structures are the most stable, the next most stable, blah, 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 and we rank them that way. The most stable ones may not be the most relevant pharmaceutically, but they're the ones you're most likely to find when you do a crystallization experiment. The ones that are maybe a little bit higher in free energy will be more soluble, but they're harder to access. But if we can find all those, then we can assign their free energies. Okay, so, but we have this roughness that I talked about, this thing that makes it very difficult to hop from basin to basin. So that's something that we need tricks to handle. And it turns out that once we have these collective variables, we put them into our computer. Of course, in the computer, we can play God. All right, so I can choose any conditions that I want because I have complete control. So what I might want to do is I might want to make these collective variables hot. If they're hot, they're going to be moving around more, and it'll be easier for them to go over the hills. All right, turns out I can do that, but if I want to recover the thermodynamics, I need to make them heavy as well. So I apply these two conditions, and then it turns out that I have equations that allow me to calculate the free energy very easily. So I'll give you an example of what a simulation like that looks like, first for a little peptide. All right, so this is a molecule containing 12 alanines. All right, so it's an alanine dodecamer. Oops. This worked last night. All right, bear with me. I've got it in another presentation, so I'll fire that up. Okay. Here we go. Oops. Okay, so this is what this is doing. And you'll see this thing fold in and out of its favored conformations. One of the things it wants to do is to form a helix, and it very easily does that. So this is enhanced F equals ma, all right, with this heating and heavy collective variables. The collective variables that we're using here, by the way, are the Ramachandran pairs of all of the alanines in this. All right, so it sometimes forms this helix. Then it can, that's actually the most stable configuration, but it can also unwind, give it a moment, and form random coils. It can form a beta hairpin. And then eventually it will, yeah, there's a beautiful hairpin configuration, really fantastic. And then it will eventually go back into a helix, which is what it really most wants to be. Okay, now if you just do a naive computer simulation of this, none of this will actually happen. So in order to do this, you need the kinds of tricks that I was talking about. All right. That's the right one. Okay, now let's do it for a molecular crystal. So this is a very simple one, usually a good starting point, which is a benzene crystal. Okay? And this thing, it turns out, has about 6 or 7 different polymorphs that it can form. Some of them are very different. Some of them are only slightly different. All right, now what we're doing here is we have a physical temperature, which is room temperature, 300 Kelvin, right? And the temperature of our collective variables, which are the shape of the cell, the orientational, and the packing parameters, are up at 30,000 Kelvin, right? So that allows them to do all this crossing of the hills. And then we run this at 2 gigapascals, which is a pretty high pressure, right? But it's one where some of the more interesting polymorphs actually start to show up. And on the time scale of just what turns out to be a few hours of desktop computer time, we can actually get this thing to visit all of the relevant polymorphs. So we get all the crystal structures. The actual chemical time is like 500 picoseconds. That's sort of the real time, all right? But it takes a few hours on the computer to get to 500 picoseconds. If we run 10 times longer to 5 nanoseconds, then we actually get enough information to predict free energies. Okay, so this thing looks like it goes through some disordered states, but it always finds another crystal structure. And as you watch this thing go, it explores a whole variety of different crystal structures. Now, at the end of the day, we have a free energy that depends on a lot of different parameters, all right? So I've got the shape of the cell in there. I've got whatever packing parameters I need here. I just call them P1 and P2, et cetera. And then orientational parameters, O1, O2, blah, blah, blah. So this is a very high-dimensional surface, all right? And you can't visualize that. You really can't visualize a high-dimensional surface. And yet, I need to find its characteristics. I need to find things like minima and saddle points on that surface. So how am I going to do that when I have all this information out? OK, so let me just call all these parameters that I've introduced S. All right? And let me introduce the gradient of the surface, or the derivative of G with respect to S, and a second derivative. It's going to measure curvature for me. So what I want to do is I want to be able, for example, to walk to a minimum. All right, so I have the surface, and if I kind of advance these S's using the gradient like this, or the negative gradient, I can actually walk to a minimum. Or if I want to walk to a saddle point, I have more complicated equations. But I can use this second derivative, which measures the curvature. And that will sort of give me the directions of the gentlest ascent from a minimum up to a saddle. And that direction is this n vector. And then I use this n vector to project the gradient such that I kind of flip its direction around. And then I can walk to a saddle point. So a picture of that looks something like this. Here's a trajectory that starts at a minimum, walks to a saddle using this set of equations, and then from the saddle walks to another minimum using this set of equations. All right? So once I have that, I can pick out the minima and the saddles, which actually are the most important points. Now, as I said, you can't visualize such a surface. It's thought that if you actually could visualize even a 4-dimensional surface, it might look something like this in 3 dimensions, but we're way beyond 4 dimensions here, right? We have maybe 10, 15, 20 dimensions. So we're not going to be able to do that, all right? So what we need to do is to learn mathematically and abstractly what the surface is. And so, for example, we use machine learning techniques to learn, as we walk over the surface, what the important points are. And we might represent it using clustering techniques or neural networks. I don't know, how many of you took the machine learning course this morning? All right, so you might have learned about some of these techniques. OK, so what we do once we've learned the surface is we represent it as a bipartite graph. All right, who knows anything about graphs? You guys ever studied any? What is a graph? Who knows what a graph is? Not a thing that you plot as an XY thing. That's one kind of graph. But what's a graph? A graph is nothing more than a collection of points with lines between them. All right? That's what a graph in mathematics is. And here we have basically 2 colors of points. So the blue points represent the minima that we find, and the yellow points represent the saddle points. All right? And then if there's a trajectory that connects, let's say, a minimum to a saddle and another minimum, sort of like what's being represented here, we get to put connections in the graph. Right? And graphs are used to represent all things, all kinds of things, not just things in chemistry, but the internet, for example, can be represented as a graph. Molecules, right, chemical graphs are actually with the structures that you draw. Those are called chemical graphs. So there are all sorts of graphs that are used. And they have interesting properties. But here, we use them to give us a picture of what this very high-dimensional surface looks like, at least in terms of the most important characteristics of it. OK. Finally, with all that information, we can turn our calculation into a diagram of the different crystal structures that I found, all right, and their relative free energies. And the way we characterize these is we use something called space groups. And a space group just tells us how things pack and how they're oriented. So this just gives you an example of 2 groups that we found, P2NB and P2NC. You can look at the shape of the unit cell that we have, and you can sort of look at the picture of what the group says the different structures should be. And by the way, a group is nothing more than a set of transformations that you can make on the elements, the objects in your cell, to tell you where to find everything else. So for example, this is a set of operations for that group. This is a set of operations for that group. And when you look at these unit cells, for example, this one, really where the molecules are very much represent where the group says they ought to be. Here, 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 well, I have that, and here, here, and here, here, well, I have that, and I have that. So it really does follow the rules of the group. And in crystallography, that is a way that you characterize crystal structures. OK. Well, of course, once you do benzene, you might want to do naphthalene. And it turns out that when you do this kind of calculation on naphthalene, you get very, very clear polymorphic transitions. It's a little bit hard to see, but as you watch this movie, you'll see this thing very clearly undergo transitions from one solid to another. And in fact, we discovered a brand new polymorph of naphthalene. It has a structure that looks like this, and it's called the P1 bar structure. So that's we're putting out there as a real prediction. All right. Coumarin, this is actually a pharmaceutically relevant molecule. It's a kind of precursor for a number of different pharmaceuticals. And that one also turns out, let's see, I hope this movie will work. Let's see if it works. No, of course not. Never fear, I have it in another presentation, so bear with me a sec. Where is my Coumarin movie? Ah, there it is. All right, let's look at Coumarin. All right, so this thing undergoes a number of very, very clear transitions. And here also we found a new polymorph. that may be pharmaceutically relevant, actually. Okay, so let me go back to the original presentation. And that new polymorph is this one here. It has a P21C structure. All right. We have to test its properties to see if it's pharmaceutically useful, but we have it. Okay. All right, let me come to something completely different now in this area, which is a very fundamental process called melting. All right. Everyone knows what melting is. All right, this is a rather horrible looking picture, and this illustrates the opposite of melting, which is freezing. This is a story that is out there. I'm not sure if it's really true or not, but the story goes like this. During World War II, up in Russia, there was an attack by the Nazis of a Russian military camp, and there were stables in this camp where the horses were kept at night. Well, when this base was attacked, the stable caught on fire, and it was the middle of winter, and there was a lake right in the middle of the base, or sort of just off the base. So the horses were spooked by the fire. They ran out of the stable, and the only place that they could sort of escape to was the water, was the lake. Now, the lake was actually in liquid form, so it hadn't been frozen, but the temperatures were well below the freezing point. So when the horses went into the lake instantly froze, and the horses were frozen in that position. And that's sort of the illustrative picture of this. Now, you might ask, is such a thing actually possible if I have supercooled water? Can it freeze like that? Okay, well, there was a Radiolab demonstration of this. Radiolab is an NPR program. Okay. And this is where, hopefully you can see that. Let me see if I can do something about lights here. No, I really can't. All right, hopefully you can see this. All right, here we go. So what they have is a vial or a test tube of supercooled water. That's there, all right? It's really, really cold. And they're going to throw the toy horse into it. And it immediately freezes. It immediately freezes, all right? Instantaneously freezes. Why does that happen? Go ahead.
When water freezes, it crystallizes, but to crystallize it, it's able to crystallize onto. The water is pure enough, it doesn't have anything to crystallize onto. When something is introduced to the water, it immediately has something to crystallize onto, and crystallizes onto that.
So what is that thing called that causes the instantaneous freezing?
Flash freezing?
Yeah, okay, but the object that causes the flash freezing is called a nucleator. It's actually an object that, where it is, the water instantaneously undergoes this transition. And there's a theory for this called classical nucleation theory. All right? Now, we were interested in kind of the opposite procedure, which is what happens when things melt. All right? So nucleation theory also describes that. And nucleation theory, again, is all about the free energy. So this is a solid sample, and we're seeing here a little liquid nucleus in there. All right? The liquid nucleus is starting to form. It's small. The theory says that the radius of that nucleus is kind of a good variable, collective variable, for determining the free energy. So there are two terms in this free energy. There's a volume term, and there's a surface term. This gamma is the surface tension. All right, and delta mu is the change, the difference in the chemical potential between the solid and the liquid phases. And at the melting point, it becomes negative. So it becomes more favorable to melt rather than to freeze. This is the density of your solid. So if you plot this function, because this term is negative, if you plot it, you actually get a very hefty barrier to transitioning from solid to liquid. All right? What happens is that as the nucleus grows, you start to ascend this barrier, and if you get to the top here, then you'll have a transition from the solid to the liquid, and the system actually melts. All right. Now let's do a little exercise here. All right, so you have here a function, and we want to predict what this point is. All right, so how many people know how to do that? What kind of problem is that, where you find a maximum of a function? Anybody here had calculus? Nobody's had calculus? Okay, it's a maximization problem. All right? We have to maximize that function. So how do we do it? Go ahead. Take the derivative and set it equal to 0. And if you do that, then you get a condition that you can use to solve for this R. All right? And what you find is that you get an expression for the critical nucleus size that you need, and it depends on the surface tension, and you can get the free energy. Okay, so physically what's happening here is that this theory says there is a competition between trying to form the liquid nucleus of a certain volume, which is actually favorable, that's why it's negative, and having an interface between solid and liquid, which unfortunately is, you have to pay a penalty for that, that's positive. So these two things fight against each other, and you get this curve that looks like this with that barrier. Okay. Well, let's see if this movie works. No, it's not going to work, so let me go back to the other presentation, and I will show you that movie. All right, this is a simulation of a system of copper atoms, 3,000 copper atoms that, again, we use this approach that I was telling you about, F equals ma enhanced, and we're going to watch it melt and refreeze a number of times. All right, very simple model. And what I'm using here is, again, the shape of the cell and some packing parameters, and that's it. Oops. I forgot when I do that, it actually stops. Okay. So let's watch it melt and refreeze a number of times. There's a melting transition. There's a refreezing transition. Melting, refreezing. And we can really get this instantaneous, we can capture this instantaneous melting and freezing, kind of like what you saw in the movie. And it goes back and forth like this. Okay. Now we can learn something from this trajectory that gives us a whole new perspective on the melting process. So nucleation theory says that you have to grow this nucleus from the inside out. What this simulation does, and why it got published, why we were able to publish it in Science last year, is it says that if you look at it very carefully, it says that, in fact, what you form as you approach the melting temperature are a bunch of little defects in the crystal. These can be vacancies where a particle leaves the crystal lattice, or it can be an interstitial where something comes in between two lattice points. And these defects turn out to be very, very mobile. They diffuse at a rate that's incredibly fast. All right? So in fact, these are some snapshots from the simulation you just watched. The first step is to form these little defects. And the first barrier is not what nucleation theory says, which is a growth of the nucleus from the inside out. It's actually a coalescence of these defects into a region from the outside in. So it's just the opposite of what nucleation theory says. All right? And then more of these defects come into the little embryo here, and you form a large nucleus, and then eventually that thing transits to the liquid. And all of that comes from looking at this free energy diagram that I have. I won't go through all the details of it. This is a projection of that, so it's kind of easier to look at this. But what we have is a brand new theory for melting, and it's exactly the opposite of nucleation theory is. So this may become the new textbook picture of a very fundamental process, which is the melting process. Okay, now I have about 10 minutes, so I'm going to finish up with one completely different area of application. So once we kind of have the ability to look at structures, we want to be able to do things like functionalize them, all right? Turn them into interesting devices of sorts. Okay, you're looking at a very simple little reaction here, which is the addition of an organic molecule to a semiconductor surface. You know, that's the basic process that we're interested in, which is really where organic chemistry meets semiconductor physics. Okay, so this is a really fundamental process, and it brings in two areas that usually don't have much to do with each other. But it turns out that you can do a lot of interesting things if you let organic molecules react with semiconductors. For example, you can get interesting chemical and biological sensors. And the way you do that is you cover a surface, like silicon, with a bunch of organic molecules. Then you come in with a scanning tunneling microscopy tip, like a tungsten tip. It's very, very sharp. It basically is one molecule sharp at the tip. And you start to knock molecules off. And you get reactive centers, and they have a very special reactivity. So they're chemically sensitive to different types of biological or chemical environments. Okay, you can actually do molecular computing with these. If you can create ordered structures like these molecular wires, then these molecular wires are pretty good electron conduits, and so you have tiny, tiny little devices that will do things inside a computer. So it's what we call molecular computing. You can passivate, so you can actually produce protecting layers on your semiconductor surfaces. And from the fundamental point of view, you might want to ask the question, well, do the rules that we usually learn in organic chemistry, do they actually apply here? Okay, well, what are some of those rules? So the typical reactions that are relevant for semiconductors are what are called cycloaddition reactions. So this is a case where, a very classic one, where I have a butadiene, it's got 2 double bonds, and I want to add it to an ethylene. And when I do that reaction, I turn the bonding structure into one which has a single double bond structure, a cyclohexene. All right, and there's an energy level diagram that is very famous for this, where you have the highest occupied molecular orbitals of one and the lowest unoccupied molecular orbital of the other, and you donate an electron pair from this to this, and the whole chemical bonding pattern rearranges. And so it's a picture that kind of looks like this, and we turn it into, for example, in this case, a cyclohexadiene. Okay, so we want to do these reactions on a silicon surface, and one of the most commonly used silicon surfaces is what's called the 1-0-0 surface. It's what you get if you just take a block of silicon and cleave it straight. All right, and so when you cleave it, of course, you have a bunch of dangling bonds. And the surface heals those dangling bonds by forming rows of silicon dimers that look like this. And those silicon dimers, turns out, have a slight double bond character. So very much like what we showed here with ethylene, they kind of act like ethylenes. Okay. Unfortunately, they're not straight like we see here, so it's not a simple process. They actually buckle. And so they form structures that look like this. And each row is the mirror image of its neighbor. Right? And chemically, that causes a charge imbalance. So some of the silicons have a net positive charge, some of them have a net negative charge, and that actually influences how the reactions occur. So let's see if I can get this movie to go. This one looks like it's going to work. Okay. Well, except it is way up there. That's weird. Let me maybe move it a little bit. Trying to make this easier to see. Does that help any? Nope. It's just coming out in a weird place. Not sure why. Okay, so given that it's doing that weird thing, let me go to, again, another presentation where hopefully it'll work better. Bear with me. See if that one works a little better. Huh, I'm perplexed. The technology is working against me. What if I put it up there? Well, it's a little better. All right, anyway, you can kind of see what's going on. So I have this organic molecule right up there, all right? And that's the silicon surface. And it's going to create chemical bonds to those silicon atoms, like this. Okay, so now I've formed 2 chemical bonds to the surface. So it is a cycloaddition reaction, exactly like what I illustrated, but with the silicon dimers acting as the receptor of the organic molecule, which was, in this case, 1,3-cyclohexadiene. Okay. Let's see if this one doesn't do that funny thing. Guess it's going to do the funny thing. But anyway, all right, here's another movie. Again, the same F equals ma kind of thing that we were talking about. What does this molecule, what does that starting configuration want to do? So again, there's your silicon surface. Okay, and the molecule sort of decides it doesn't like where I put it initially, so it takes a walk over to the other row and says, there's a place I can react. And it forms a chemical bond. But in this case, it actually forms chemical bonds between 2 neighboring dimers within one row. So it's a different reaction product, actually. And let's look at one more. Okay, so again, here the molecule is starting over one of the rows. Decides it doesn't really like where I put it. Takes a swim, in this case, over to the other side. And I get a bond forming there. And then it really stretches and it bridges two rows together. All right, and I get a product that looks like this. Now, all of these products, turns out, can be seen experimentally. Okay, there's a technique called scanning tunneling microscopy. There, that actually images these things. All right, and the images just look like these bright spots. So here you see, and these are the experimental images, and here you see the silicon dimers, the various reaction products. Here's one where we form this addition on one dimer, the cycloaddition product. Here's one where I actually bridge two dimers together in a row. All right. Actually, this is the one where I'm bridging two rows together. That's the B product. Here's one where we're actually bridging two dimers in a row. That's C, and there are actually two of them. And then there are a variety of other products that you get. So unfortunately, silicon is really fascinating in the fact that, in the sense that you can form all these different products with a different distribution. But in terms of forming, let's say, an ordered structure, silicon, molecular wires, all these products that you can get will compete with each other. And so this is not a very good surface for that. Okay, well, again, coming back to this picture of free energy, we can characterize the reaction by looking at the free energy as a function of some coordinate, all right? And the coordinate that we use, in this case, turns out to be the distance between that center, so these two outer carbons, and the center of the silicons. And when you actually plot that, you can actually do that by doing a little integral here, then you get a nice barrier. It's not that big. It's about 10 kilocalories per mole, and then it's downhill to the reaction product. So we wanted to use this idea to see if we could engineer a better surface for forming ordered structures, and we did. And the one that we looked at in this case was a silicon carbide surface. Silicon carbide is kind of the darling of the semiconductor industry in that it's incredibly strong and has a very, very high conductivity. And we took a particular surface of the silicon carbide sample in which the dimers that I form, so I have these rows of dimers, but they're not silicon, they're actually carbon dimers, and they're triple bonded. So there's actually a C triple bond C structure that we have. Now this surface has been studied before, but very minimally, and it certainly hadn't been tested for creating organic layers. So this was really a first attempt to engineer a new kind of reaction. Okay. And so we used these reaction profiles to tell us what is the likelihood of all the different reaction products that we had. For example, the one where the molecule just adds to one dimer, and then you have the products where it bridges two dimers in a row, the inter-row and the inter-dimer intra-row, so the ones where it bridges two rows together. All the things that we saw in silicon can be studied here as well. And if you look at these reaction profiles, you see, for example, that there's only one that has a very low initial barrier of about 8 kilocalories per mole. All these other ones have barriers of like 30, 40, even 50 kilocalories per mole, up to 80 kilocalories per mole. They're all going to be highly disfavored compared to this one. And this one is exactly the one that we wanted, the one where the molecule sits on one of these dimers. So when we actually then threw a whole bunch of molecules on the surface in the computer, it formed a perfectly ordered row like this. So we have these nice ordered rows of the cyclohexadiene, and those are molecular wires. We're now testing them to see if they have good conductivity, so they actually could be used as a real molecular wire. And all that has to happen for that to be the case is that the orbitals that are formed above the molecule, like the pi orbitals, they just have to be close enough that an electron can hop from one to the other. All right, so that's something that's ongoing. All right, I'm about out of time, so I'll just thank the various collaborators that I have on this. So all the structural stuff was done with students of mine here at NYU, at Lawrence Livermore, and I have collaborations in Germany and in India, so I'm working with people there, and I spend a lot of time in those places. And then functionalization was done with, again, former students of mine, most of whom have graduated except for one who's coming up for graduation. All this work was funded by the National Science Foundation, the Alexander von Humboldt Foundation, the Army, as it turns out, is interested in much of this, and, of course, NYU. Right? So let me stop here. I'll take any questions that you have. Do you have any questions? All right. Thanks.